Welcome. This is our last lecture, lecture 12, and we are going to talk about cluster analysis, which is basically an unsupervised learning technique. Okay, so basically, I'm going to start with distinguishing between supervised versus unsupervised learning. Then I'm going to talk about cluster analysis, a specific technique called the K-means, and briefly we'll close this session by talking about hierarchical clustering. Okay? There are some applications, these two papers, some references, sorry. These two papers on our Google Drive folder. Okay? So basically, most of the models that we have seen so far deal with prediction of y given x. Okay, those are called supervised learning. Now we are going to treat models for x only. So we don't have the response variable y anymore, and these techniques are called unsupervised learning. Okay, so in supervised learning, one is interested in properties of the distribution of y given x, such as the expected value of y conditional on x, and not on the distribution of x. And as opposed to unsupervised learning, where the interest is primarily on properties of the distribution of x. An example is the condition expectation of x. And examples of supervised learning are linear regression, logit, probit, neural networks, support vector machines, so on and so forth. Whereas like factor models, principal component analysis, and clustering, the topic of today's lecture, are examples of unsupervised techniques. Okay? So what's clustering? Basically, it's a collection of tools to help us to group data into different subgroups. And these subgroups are called the clusters, okay? Such that data points in the same groups are more similar than data points in different groups. Okay? So why would we do that? Like way of summarizing information, like descriptive statistics, to see like if averages or variances differs among different groups. So we can model heterogeneity in our data, and we can use these heterogeneity like to tune different marketing strategies, different investment strategies, and many possible applications. Okay? And also, it helps us to discover new patterns. Maybe these clusters kind of not obvious. So we may have, imagine that you are in a big corporation, a big bank, you have millions of clients, and then you figure out that there's this group of clients that are more tuned to a very specific kind of investment, and you have never realized about that. So these techniques can help us to uncover structure in the data set. Okay? So applications in marketing, land use, insurance, urban planning, and also earthquake studies. Okay, so we can like observe earthquake epicenters should be clustered along continent faults. So we can use that to help predicting seismic activity. Okay? So one question, where should we place cell towers? And we want to ensure that no building is more than 3,000 feet away from a cell tower. Okay? So a good clustering method should produce two things. The first one, high intra-class similarity. So observations within a specific group should be similar, and low interclass similarity. Individuals in different groups should be different, but then we have to define what does similar and different mean. We need a metric to quantify how close are two observations. Okay, so the quality of a clustering result, the clustering result depends on two things: the similarity measure and how we implement the method, the way we implement it. Okay. Uh, so the quality of a clustering method is also measured by its ability to discover hidden patterns. Because if a cluster just gives us the obvious thing, then maybe it's not useful at all. So you want to discover this, we want to unhidden the patterns. Okay. So for example, here, how to define what's similar. Okay. Food for thought. Okay. So let's go to the math. Okay. So we have a collection of data, X. Okay. And we like to cluster on n times p matrix consisting of n units observations of p attributes. Then we denote generically by xil, I indexes n, l indexes the attributes. Okay. So then we define for each pair ij a measure of dissimilarity along the ELF attribute. So we have this function rho that takes the value of the ELF attribute of observation I and observation j and comes with a dissimilarity measure. Okay, and when we then combine those attributes specific dissimilarity with a weighted measure. So we define the weights. These weights must be positive and some one. Okay, and we have the total dissimilarity measure for a pair ij. Okay, will be the weighted combination of the feature of the attribute specific dissimilarity rho L. Right? And how we do we choose the rho function? It should be continuous for real value attributes you can define for any monotone increasing function like rho of x, y, like a g function of the absolute difference between x and y. Okay, we can also make it ordinal for an attribute that belongs to a finite set O1 to OM with some intrinsic order like grades A, B, C, D, E, F. We can convert it to numerical values by doing lowercase u minus half divided by m, where u is one of the m different classes. Okay, and then we treat it as a continuous attribute. Nominal, or also called categorical. So for an attribute that can belongs to the set n1 to nm with no specific order, okay, like single, married, divorced, then we can choose the rho will be equal to 1 if x is different from y. Okay, so those are kind of three different measures of dissimilarity. Okay, so once we define D, we can construct the n times n symmetric non-negative matrix of dissimilarity where each input dij is the d function of xi, xj, okay, where I and j indexes the observation. Note that x are a vector here because it belongs to the whole attribute. So this is the d function. So it's the weighted sum of the rho, the feature-specific dissimilarity measure. Okay? So, and then the total dissimilarity for a data set is the sum over the dij's. Okay, where we can write it is in a matrix format that iota d iota. And so the total dissimilarity is the within plus the between dissimilarity. So let's k be a number equal or greater than 1 and the number of clusters. Let's assume that we know the number of clusters. And let AI denote the assignment of unit I to a cluster. So if AI equals to k, lowercase k means that the unit I was assigned to cluster lowercase k, right? So if we have the assignment of each observation to each cluster. Note that an observation can belongs to only one cluster. Okay, there are also a different literature on fuzzy clustering that you have like a probability of being in one cluster or the other, but here either be one cluster or the other, right? So we have this vector A where we assign each observation to each one of the capital K clusters. Okay, so we can decompose the total dissimilarity T, which is the sum over all the ij's, will be the dissimilarity within a cluster plus the dissimilarity between a cluster. So the blue term we're going to call WA, that means within, and BA, which means between. And W and B are known as the within dissimilarity and between cluster dissimilarity. And we have the identity that T equals to W plus B. Okay. T does not depend on the assignment. Okay. And T is a constant given X and D. Thus, minimizing W is equivalent to maximizing B, right? Because T is given once we define what's our dissimilarity measure. So let's look to the k-means method. So the k-means algorithm is one of the oldest and still very used, very popular in different areas method of doing clustering, of doing cluster analysis, and it's very simple. Okay, that's the main advantage, is that it's really, really simple. So it applies to situations where all the variables are of the continuous type or transformed to be continuous. Okay, and we are going to use as measure of distance the Euclidean distance. So if we have like two observations ij, d is defined the sum over the attributes of the square difference between two observations. So it's the L2 norm squared of xi minus xj. Okay. So let's case the number of cluster again. For a given an assignment A, okay, we can compute the dissimilarity variation within a cluster given the attribute A as the expression that you have on your slide, and this will be proportional to the number to this expression where n is the number of points in the kth cluster and x bar is the called centroid. So it's the mean attribute on that cluster. Okay, and then we can basically show that this term here that we have here, right, which is the one here, with some algebra, it will be 2 times the number of points in a cluster, okay, times the distance between each point and the centroid of that cluster, of course, with the respective summations, right? So the algorithm, what the k-means will do, the k-means looks for an assignment, optimal assignment that we're going to call A star, that minimizes the within cluster variability. We want that observations within a cluster be very close to each other, and we measure this degree of closeness by the distance, the Euclidean distance from the centroid. Okay, and we are going to do this in a 2 steps iteration until convergence. So we choose an assignment A, we compute the mean of each cluster centroid, okay, and given the centroids, we find the new assignment A given by the expression that we have in green on our screen. Okay, and we continue iterating these two steps until convergence, until our cost function do not change anymore. So it looks like the target is like the centroid, right? We want this distance to be close to the observations to be close to the centroid of the cluster. So like the cookbook, we have like points labeled x with two attributes, x1 and x2, like having like three clusters, the brown, the green, and the blue. We pick like k equal to 3. We have the centroids are um, red the red points. Okay, we can like initiate just by random sampling k centroids. We assign label to each data point based on the closest centroid. Okay, we calculate the new centroids of the average of the points in each cluster and repeat steps 3 and 4 until the within variation stops decreasing. So let me repeat. We have the data, two attributes. Basically, we say there will be three clusters. We select three centroids randomly. Okay, we initiate by random. Okay, no information about where are the centroids. Then we assign each observation to the cluster where the distance to the centroid is the smallest. And then we recompute the centroid and we iterate this procedure. Okay, so really, really simple. Okay, to be implemented. Okay, so that's several iterations. We have the initial centers here, and then the first iteration, and then the colors means indicates the assignment, the second iteration, third iteration, fourth iteration. You see, they're very clearly define the clusters. Okay, so it's very interesting to see how the clusters are being formed. So properties of the k-means algorithm. Steps 3 and 4 reduce the value of the sum of squares, so convergence is assured. Okay. But the result may represent a suboptimal local minimum instead of a desired global minimum. Okay. So because the solution will depend on the starting value of the centroid. So you have like here three different setups with completely different assignments depending on the starting location or the initial centroids. Okay? So one way to kind of remove these is kind of trying different initial values and see how things change. Why do steps 3 and 4 reduce the value of the sum of squares? First, we can look at that as an enlarged minimization problem that we are looking for these assignment rules and the M's, what the optimal centroids, okay? And we are going to find the assignment alpha star this way, okay? And know that for a fixed assignment, the K clusters means the centroids are the optimal solution for the quadratic minimization loss. Okay? But that's the mean. Okay. So for a fixed assignment, M equals to X bar solves the problem. So a final local solution is obtained by alternating between A and solving for the optimal M's, and given the new M, solving for all X's for the optimal and new A. Okay. So this way we can assure that we are reducing the sum of squares. So is it possible to find a global minimum? No, there's no guarantee, but we can improve the single naive solution. So try multiple initial solutions and choose the solution with the smallest within cluster sum of square. Okay. this with parallel computing. It's pretty easy to implement. Um, and a paper in 1979 proposed an improved algorithm. They look for the local minimum subject that there is no single switch of an observations from one cluster to another clusters that will end up decreasing the objective function. Okay, so it's a little bit more complicated, but it's another way of implementing uh, a better solution. I like the first one. I think it's natural, and with computer power, with parallel computing, it's very easy to be implemented. Okay, so scale matters in k-means. So the algorithm minimizes the total square sum across all attributes. So if we replace xij by 2xij, then this attribute will count more. Okay, so future j will influence more in defining the cluster assignment. So a quick fix, standardize the attributes. Okay, so that's the good practice to work with standardized attributes. Okay? So how to choose the number of clusters? K-mean is easy to implement and fast to compute, but we need to specify the number of clusters. Sometimes K is obvious, like where to locate my K delivery trucks to maximize coverage, so you know where to install K antennas to reach the most clients. Other times, K is a problem itself to be addressed. How many customer segments do you want to target? How many access to the highway we need to minimize traffic jam? So most often clustering is a kind of exploration exercise. So we should K that makes the most sense to us, right? But there's also some data-driven methodology. So we can, for some maximum number of clusters that we allow, like big M, we can find a criterion to choose one of them. But that can be tricky. Uh, let Wj be the within cluster sum of squares with J clusters, and we always have like um, the highest the number of clusters, the smallest is the within cluster sum of squares. Okay, so we will always choose to have M clusters. It's like including more regressors in a regression. If we do not penalize for the complexity, no way. Okay, uh, so and we when we don't have a kind of out of sample thing, so unlike supervised learning, we cannot do cross validation. Okay, so we can use a kind of information criterion. Okay, so the deviance is just the sum of squares, like in regression models, and we have a way to compute degrees of freedom with n variables and p attributes. Okay, uh, and j clusters, the total number of parameters defining the centroid for each cluster pj. Okay, is the degrees of freedom, it's the number of degrees of freedom. So we can compute like kind of AIC, BIC type of formulas that will be P times J plus WJ for AIC, and BIC P times J times log N plus 2WJ. And we select K star as the argument that minimizes the IC. Okay? And but there's no big theoretical justifications. So they don't have the same properties as we have for the linear regression models. Okay, so it's kind of you should be aware and take care and try different values and see how different your results are, and if your clusters are making sense, and if it fits the problem, if you are not kind of overestimating the clusters, so you like overestimating heterogeneity and things like that. Okay, so BIC versus AIC. So we have here P attributes, 6,500 observations, 3 clusters, M equal to 200, like the maximum. So BIC would suggest 50 and AIC would suggest 130. They are very different and both sounds too high. The truth is that we just have 3 clusters, so beware. Okay, so take care. It's not easy. So as I mentioned before, sometimes better to use intuition and what do you expect, interpretability, because determining the number of clusters is not something that's easy. All right, so to end up, let me briefly talk about hierarchical clustering. Okay? So k-means has 2 main drawbacks. It depends on a pre-specified number of clusters, and the solution depends on the initial state, the centroids. Okay. Hierarchical clustering is an alternative that mitigates some of the problems of the k-means, and it does not rely on an underlying model, nor does k-means, of course, so it's not an advantage itself. The clusters are nested, so it's kind of you start with a division and then subdivisions and goes like this, like in the tree, similar to a tree. Okay, so we do not need to choose the number of clusters beforehand. Okay, and no need to start to select starting positions. Okay, so it provides a deterministic solution. It's not a random solution. Okay, and there are 2 types of hierarchical clustering algorithms: the bottom-up approach, the agglomerative. Okay, so we start with every point being its own cluster, and then you're going to repeat it. You're going to merge the 2 clusters that have the smallest dissimilarity until there is only one cluster. Okay, the divisive, that's the top-down approach. Okay, we start with all points in one cluster and we split the cluster into 2, resulting in the biggest dissimilarity until all points are in their own cluster. Okay, the first one is simpler. We are going to focus on that one. Okay, so we have like here 5 points. Okay, so we're going to merge 2 points that are close to each other, so A and B, A and C, D and E. Okay, the next one are D and E, and the third one is like B, A, and C, and the final one are all points. Okay, so and so what we do now, uh, so how can we visualize the hierarchical clusters with the dendrograms? Okay, it's just each node will represent a cluster, and each terminal node is a singleton, a cluster containing a single data point. The root node is the cluster containing the whole data set, and each internal node has 2 children nodes representing the clusters that are merged to form it. Okay, so in our case here, we have all the data. That's the cluster with the dashed line. Then we have like a cluster with D and E, a cluster with A and C, a cluster with A, B, and C. Okay, and here we can come and choose which are the clusters that makes more sense. Okay. So how we're going to construct the agglomerative Hayes. At our first step, each cluster is a single point. So we start by merging the 2 observations that have the lowest dissimilarity. Okay, and after that, we need to think about the similarity not between points, but between clusters, the set of points. Okay, and the dissimilarity between 2 clusters is called the linkage. So given 2 cluster sets A and B, a linkage is the similarity measure, rho of A and B, how different the points in these clusters are. Okay, so for given the similarity measure D, we can construct the linkages. One is the single, so it's the minimal intercluster dissimilarity. We compute all pairwise dissimilarities between the observations in cluster A and the observations in cluster B and select the smallest one. That's what we have on our screen. Or the complete, where we take the maximum. The same thing, but we take the maximum, okay? Or the average. take the average of the dissimilarity, or we take the centroid, the distance between the two centroids. Okay, and in single linkage, it's also called the nearest neighborhood linkage. The dissimilarity between two clusters is the smallest dissimilarity between 2 points in different clusters. So you have like two clusters, A and B, A green, B yellow. We have the dissimilarities, the Euclidean distance, and a single linkage between A and B is the smallest distance between 2 points and A and B, and here it is defined as this distance here. Okay, so we have here a setup with 6 observations, 2 attributes. The distance measure is the Euclidean distance, so cutting the tree at h equal 0.9 gives the cluster assignment by the colors. Okay, so what's h equal 0.9 is the height, right? Height of the dendrogram. Okay, so it's kind of, so here we cut here, so we are going to take these 2 clusters. Okay, one cluster with few, like 3 clusters, a singleton here, this big one here, and that one here. We can select where we are going to cut. Okay, in complete linkage, we look at the maximum. That's what we're seeing here. The same thing, but instead of the minimum distance, the maximum distance. And that's what we have. Okay, if we cut at h equals to 5, that's what we observe. Okay, so problems that we can see here: single linkages sum from chaining. In order to merge 2 groups, only needs 1 pair of points to be close, irrespective of all others. Okay, and cluster can be too spread out, not compact enough. Complete linkages surface from crowding, because it's based on the worst case dissimilarity. A point can be closer to points in other clusters than points in its own cluster. Okay, clusters are compact, avoids chaining, but not far enough apart. The average linkage tries to strike a balance. It uses the average pairwise dissimilarity, okay, and it avoids chaining and crowding. Okay? So that's the similarities between 2 clusters in the average similarity over all points in opposite clusters. So that's we are measuring the distance between the green points to one yellow point here, and that's the final dendrogram and the clusters. So different linkages, you may have different clusters. The average is pretty much similar to the complete, but very different from the single. Okay. So results of average linkage can change if we simply apply a monotone increasing transformation to our dissimilarity measure. So instead of d, we choose d square. We can have a problem. So if we are not sure precisely what dissimilarity we want to use, this is a problem. The single and complete linkages do not have this problem because min and max are invariant to monotone increasing transformations. Okay, so you see the average link distance if we use the Euclidean norm or the square norms. Okay, and so left and right panels will be the same if we use single or complete linkage. For average linkage, the results can differ. So there's no free lunch, so it's a matter of playing around different linkages and see the result. So my recommendation is that, okay, you have k-means, you have hierarchical clustering, you try different techniques. Of course, this is just the top of the iceberg, and we could have full course on clustering methods. I just wanted to give you an introduction to these techniques. So thank you very much. Thank you for attending Fin 580. It was a great pleasure. And see you all on our final live session on